connected with the industry, doing applied research. That's actually the amazing part of it. I mean, I myself also like applied research, so want to be connected with the industry. They are even better than me. I mean, like doing all kind of crazy stuff, very large group, and I'm sure he has a lot of good things to talk about today. So Qammer, very nice to have you here. Always actually invite him whenever he's available. He's my dear and near friend. Okay.
Thank you. Thank you, Professor Arsalan, for the kind introduction. So I thought, how should I start my slide? So I thought this is very nice quote to start with, especially for countries like Turkey, and I'm from Pakistan as well. And let me tell you a story. I know Professor Arsalan since 2013, when I started as a research scientist in Texas A&M at Qatar. And let me tell you one thing. I never saw a hardworking person. Of course, intelligence is another thing, like him. So thank you so much, Professor Arsalan, for inviting me, and it's a real honor to be speaker here. As Professor Arsalan explained, from last 2 days, you are listening a lot about 6G, what 6G will look like, what will be in 6G. But the real question is how 6G will be able to work. And my talk today is around some of the enabling technologies which we are working in University of Glasgow, but due to limitation of time, my focus will be only on reconfigurable intelligent surfaces, but I'll touch the other few topics as well. And I think I'll skip this slide because you have heard a lot about it, that how mobile communication has evolved over last 40 years. And with 5G, the real revolution came where we started talking about an ecosystem, that the mobile communication will be changing an ecosystem instead of only based on mobile technology. And you can imagine that how this thing is penetrating in our life. We can live without food and water, but we cannot live without this technology nowadays. We cannot sleep without it, we cannot wake without it. And around 67% of the global population is using internet. And an average user spends around 7 hours a day on using internet. And up to 5G, many of you know that we set up the KPIs first, and then we start working on the technology. And 5G, we were in Mobile World Congress together. There was a big challenge for 5G that operators and investors are not getting return on investment, because now they are looking for use cases which can use 5G. So we thought that instead of using bottom-up approach for 6G, let's take top-down approach. Let's not talk about KPIs. Let's talk about use cases. What is the use case which cannot be enabled by 5G, and why we need 6G? What are the use cases which need 6G? So one of the use cases which we are working is called Internet of Senses. I don't think so I need mic because I'm loud enough. So we all know that we have 5 senses. Hearing, mobile phone, already helping us, vision, video calls, haptic. You have seen that there is so much robotic technology coming out where we can do touch, but there are 2 other senses, smell and taste, which we cannot teleport. So I'm sure many of you have seen that we are seeing holographs, right? But think about if we can teleport all 5 senses from point A to point B, which will enable us to have a real holographic transmission from point A to point B with all the 5 senses. But let me tell you, this is not simple. if you want to teleport 5 senses from point A to point B, you need to first digitally create those senses, and then you have to teleport all those 5 senses from point A to point B in almost real time. And let me tell you that 1-inch scale in palm of my hand needs at least 1 gigabit per second of the data. So imagine if I want to teleport a complete hand from point A to point B, I want to teleport smell and taste as well, with other 2 senses as well, in total 5 together. I need ultra high throughput, ultra high bandwidth, ultra low latency, which is not possible by 5G. So we made a case here that this is a use case which is called Internet of Senses, which cannot be possible with 5G. Okay, sorry. Okay, I'll do that. Because I cannot use my hands in microphone, so that's why. So, no, that's fine. So I don't need to tell you what 6G is, but we have made the case here that there is at least one use case I just presented which needs 6G. And now, in our hub, we are trying to work on some of the enabling technologies for 6G, which includes antennas, which includes intelligent reflective surfaces, and quantum as well. But today, I'll be focusing only on intelligent reflective surfaces. Before going into that, one of the things which is being discussed in the community around is, and you have listened as well, the prospective band for 6G is terahertz. And antennas are ears and eyes of any wireless communication system, so they need to be right. So in University of Glasgow, we are developing various world-first antennas working at terahertz by using 2D materials, because conventional materials cannot work at terahertz because of degradation in efficiency. So we have developed various combination of material-based antennas, including graphene, aluminium, perovskite, and some other kind of 2D materials to come up with recipes to make these terahertz antennas. And why we are able to do these antennas are devices, because in University of Glasgow, we have world-class facilities, including James Watt Nano Fabrication Center, which is 1,400 meters square clean room. And then we have a characterization and testing facilities from 10 megahertz going up to 1.1 terahertz, including automated, semi-automated probes, on-chip measurements, and also 6G signal generation as well by having load pull measurements. Now, let's come to the main focus of this talk, which is intelligent reflective surfaces. So for some of the students, I just want to explain what it is with a nice example. This is Hunterian Museum in University of Glasgow, which was established in 1451. So imagine I want to provide a coverage to the user who is using mobile phone while sitting here. So she's using mobile phone, but whatever signal is reaching to her, there is no direct path. It is either through reflection, scattering, and diffraction. So the signal reaching to her either adds up constructively or destructively, and ultimately quality of service will reduce. But imagine if I have something on a wall, like a mirror. Imagine I have something on a wall like a mirror which can reflect the signal, delay the phase of the signal, and focus the beam on a user. This will ultimately enhance the quality of service. So these intelligent reflective surfaces are nothing different from which has been done hundreds of years ago, that how we control the light. So we used to control light by using mirrors. Similarly, these intelligent reflective surfaces are mirrors for electromagnetic waves. So we use these mirrors to control electromagnetic waves. And their applications are immense. In addition to communication, you can use them for coverage enhancement, you can use for healthcare sensing. I will tell you about that later on. You can use it at railway station, so on and so forth. So in this talk, I'll be talking about some of the reconfigurable intelligent surfaces design we had, its application in communication, in sensing, localization, and the big hype for 6G, integrated sensing and communication. So I'll show you towards the end, world first integrated sensing and communication demo we just developed explicitly for you, Professor Arsalan. So these are some of the test beds which we have developed in University of Glasgow. The first one is 1-bit or binary reconfigurable intelligent surfaces. When I mean binary, it means you can change the phase of incoming signal either by 0 or by 180. The phase difference is 180 degree. So how you work on these surfaces is that you start with a unit cell design, which is the basic building block. And this is on the right-hand side on the top, you can see a unit cell design, which is a patch antenna cut into half, and ground was placed at the back so that we do not have EMI interference. And then we replicate it to make one tile, as you can see on the left-hand side. And the switching element which can turn on or turn off these unit cell is a pin diode in this case. Please remember that we are using pin diodes here. Later on, I'll tell you why we use pin diode and why don't we want to use pin diode. So we used a tile-based approach, as you can see, so that you can put these tiles in any number, in any shape you like. So our first test bed was 16 tiles structure. As you can see, these are 9. But the total dimension was 1.3 cross 1.3 meter. And each unit cell had a one switching element, the pin diode, as you can see on the left-hand side at the back, to turn on the unit cell. And then these were cascaded to make 4,400 in total elements. And the advantage of having pin diode behind each unit cell was that you can control each element individually. And this individual element control can give you a near field performance. Whatever you see in literature, 95% of those rays works in far field. But they cannot work in near field because you cannot control individual element. And this race can work in far field as well. It can go up to 50 meter. Then the second design was 3-bit unit cell design. So when I mean 3-bit race or unit cell, it means you can change the phase by 2 raised to the power 3. So you can have 8 different phases with a phase shift of 45 degree. And important point to mention is that these RISC designs are in sub-6 gigahertz because we work with British Telecom and their interest is in 5G frequencies, which is 3.75 gigahertz. So then we made a 3-bit race, as you can see, the unit cell design. And then again, we use a tile-based approach. One of the uniqueness in this design was that the previous race design I showed you, it was each unit cell control, means that you can control each small bit. But because that cost a lot, so what we did in our new design, we made a column control. Column control means that the whole column, you use only 3 pin diodes instead of using each unit cell. The benefit of that was reduction in efficiency and also a great reduction in cost and complexity. So this had in total 2,300 unit cell. This was, of course, the control circuitry at the back where we were using pin diodes. Now, the question is, okay, we made these designs in simulation, measurement, does they actually work? The first thing is, we tested this in our anechoic chamber. So this is 3-bit race, where you can see the top figure shows the amplitude, and the bottom figure shows the phases. And there was a great agreement between simulation and measurement-based phases, which validates that, okay, our design works. But does it actually provide the coverage enhancement or not? That was the next question. So we did indoor trials for various scenarios in James Watt School of Engineering, which includes corridor, lobby area, multi-floor scenario, where you can see that if we take an example of corridor junction, there was a transmitter and receiver was placed in various locations where they cannot see the transmitter, and the relay was the developed race. Same was for other cases as well in lobby and multi-floor scenario. And results were very encouraging. We got a coverage enhancement of, on an average, around 20 dB for indoor scenarios. Please note one point here, that we are using directional horn antennas. So I'm emphasizing these points because I'll talk about these points later on. So we were very happy. We went to British Telecom. Look, we got, like usual researcher, we got a 20 dB gain, coverage enhancement. They asked us first thing, that what is the total power consumption for your structure? And then we thought, okay, we didn't think about that. And the power consumption was around 18 watt for those 4,400 elements, because we were using pin diodes. British Telecom was not happy. Our first structure was vertically polarized, second one was horizontally polarized. They said, we want dual polarized. Then we went back and we had to change all our design. So then we came up very good solution that if we use varactor diodes, because all the power consumption was because of the electronic circuitry and switching elements. So we use varactor diodes because varactor works in reverse bias and power consumption is very low. So we made a new design where we use varactor diodes, and of course you have to change unit cell design as well. Ultimately, the power consumption reduced from 18 watt to 8 milliwatt, which was very encouraging. And also, our new design was dual polarized because we don't know the incoming signal polarization. So your design need to be dual polarized so it can cater any kind of polarization. So this is the new unit cell design, which was varactor based with vias. And another benefit we got here was, in addition to the previous design, that in previous design with pin diodes, once you have designed the race for a certain frequency, you cannot change it, because pin diode does not change with voltage. So here we use varactor diode, so you know that if you change the voltage, you can change the capacitance. So ultimately, you can change the center frequency as well. So this new design, which is our latest design, gave us multifold benefits ranging from dual polarization to controllability. And another added benefit it provided us was beam steering, because you can change the voltage, so you can steer the beam as well. So these are the simulated results for a fixed transmission signal, and you can see that we can change the phase from 0 to 180 degrees. So we can steer the beam. But again, you know, this is just simulation. So we went to University of Southern California. We used their channel sounding measurements to validate our simulation, where you can see that there's a very good agreement between simulation and measurement, where you can steer the beam from 0 to 180 degree. So I think I'm talking too much technical, but this video will explain a bit better what I meant when I say that how RIS is helping us. Oh, there's no audio. There's no audio. Yeah, there is audio. So I can say in parallel. So what we are trying to do here is to demonstrate a video link over RIS. The transmitter and receiver were totally in non-line of sight to each other. Unit cells, and it is working in sub-6 gigahertz. So transmitter and receiver are in different rooms. Of course, we were using horn antenna and USRPs. So currently, this reconfigurable intelligent surface is not configured. And you can see, as you can see in the screen on the right-hand side, at this stage, our IRS is not working and the signal quality is so low. So now we will configure our IRS. As signal quality is so low, video is not being streamed. So as soon as we have configured our IRS, you can see that signal strength is going up, and then video streaming will start. And our signal quality is increased by around 25 dB by using the intelligent reflector. And this video demonstrates
Hello everyone, this
the beam
is
steering
our intelligent
capabilities of
reflective
this
surface
reconfigurable
with around
intelligent surface. So
4000
this is
elements,
actually
which is scanning the beam in
a
complete
beam scanning going from
360
0
degree
to 90
in free
to 180
space.
degree. You can
As
see,
you can see that
then 270
wave
degree and
is
360. So we can
rotating
control and steer
from
the beam. We can do beam
0
forming,
deg-
which we all demonstrated. No, everything was working fine. I was giving a keynote in one of the conference, and somebody said to me, whatever you are presenting, this will not work in reality because you are using directional antennas, you are using a controlled environment. Will it work in reality? This made us think again, okay, let's demonstrate in real world environment. So these are world first trials with RIS, with a commercial network. So we work with British Telecom in a industrial park to use their actual network to test the performance of our reconfigurable intelligent surfaces. So as you can see on the right-hand side, so this is the mast we were using. This was the MIMO antennas being used by British Telecom. So this is the transmitter array location. And we selected two zones, Zone A, Zone B, where we placed receivers at various locations, and RIS as well, to see if this RIS will work in reality or not. Of course, it includes a long experimental setup starting from calibration and months of planning. So I'll skip that. So this is what is important. So this is the zone A, where we placed RIS and receiver at various locations one by one. This is the reference signal when there was RIS which was not configured, but as soon as we configured the RIS and optimized the performance, you can see that we have enhancement in receive signal. There was a gain. This was at location 1. We moved to location 2. The gain was around 7 dB. We moved to location 3. The gain was enhanced to around 10 dB. So this validates for the first time in literature that yes, RIS works with a commercial network as well and has a great capability. Of course, we did various other experiments. You can see that here at the bottom right figure, we have a gain enhancement of around 33.6 dBm, capacity enhancement of around 50% at a transmit power of 33.6 dBm. So, and gain, you can see these are 3 different positions which are plotted together. We have a gain enhancement from 7 to around 15 dB. And then, of course, this was a very thorough campaign. So when we moved to location B, of course, we got excited as a usual researcher. In zone A, everything was working perfect. But when we went to zone B, there was no gain improvement. And we were very disappointed that what happened, that RIS is not working here. And of course, we looked back at the physics, and then we came to conclusion that there was big buildings there, and there were no reflections which were reaching to the RIS. Of course, there was no signal reaching, and of course, then there will be no coverage enhancement. But this is still work in progress trials we are doing and processing that, where we tested various scenarios, including changing the RIS angle, also many other scenarios. But the conclusion was that, yes, RIS is a potential game changer for future 6G communication, where you can have a coverage enhancement of around 10 to 15 dB. Now let me move to the next point, which is a very interesting and unique application we are working on, how we can use RIS for sensing. So I'm sure you have heard a lot about integrated sensing and communication. So we are working in sensing from almost 10 years. The idea is that how we can move from a doctor-centric healthcare to patient-centric healthcare. What I mean by this is that currently, if we have any kind of issue, we go to doctor, they prescribe us, and then we follow that approach. But the new concept is that bringing hospitals to home. So we will have smart homes where there will be various kind of sensors, including point-of-care sensors, environmental sensors, nanosensors, and also, most importantly, these ambient radio frequency signals. They will all work together. We'll collect enough information from them, then we'll apply AI and machine learning to that to do proactive decision making, which is the need of hour. Because currently, you go to doctor, if something happens to you, sometimes it's too late. So in interest of time, I'll focus only on ambient RF sensing. So what I meant by that, so we work very closely with health professionals as well and care homes, where elderly people do not like to wear sensors and smart watches and any other kind of stuff. But our goal is that can we use Wi-Fi and mobile signals around us to monitor people's health, because they are available everywhere and you do not need to deploy new structure. So from last 10 years, we are working with that. But there are certain limitations with that technology, that these ambient radio frequency signals, you cannot control them. So I can monitor someone's vital, which includes heart rate, breathing rate, or activity pattern, if it's a single subject. But if there are multiple people in a room, can I do that? Number two, if I want to increase resolution, can I do that? Number three, if I want to localize the target, can I do that? With the current technology, we cannot do that. But what we did, as you might have guessed on the right-hand side in the figure, that we use these intelligent reflective surfaces to control the beam, these ambient radio frequency signals, so that we can do all these which I just mentioned. And we have demonstrated this by publishing in Nature that how this race can help us to solve the problem of ambient radio frequency sensing. So for that, of course, we did some kind of controlled experiments in our lab. As you can see, it's a lobby scenario. Transmitter and receiver cannot see each other. The user was performing some kind of activities in this zone, and RIS was helping in this case. And there were various scenarios which we tested, but results are which matters. So when there was no RIS, the classification and detection accuracy was random. There was nothing. But when we turn on the RIS, we can control the beam. Ultimately, performance was greatly enhanced. And this opened a new door for many people to work on, and they are following us. And also, we are trying to do something similar here. During pandemic, you have noticed that everyone was wearing the mask. So one of the challenge, this is related to hearing aid devices. So one of the challenge with hearing aid devices is that they have a cocktail effect. So cocktail effect is that there is a noise coming because those hearing aid devices are not tuned to every environment. They have a noise threshold which changes according to the environment. So the listener have a cocktail effect, and they do not like to wear those hearing aid devices. So the solution to that is multimodal sensing. So Google have glasses which can do your lip movement through a camera. So, but the challenge during pandemic was that people were wearing masks, so camera cannot read those lip movement. So what we did that we used our ambient radio frequency sensing technique to read under the lips, the movement of the lips, because RF waves can penetrate. And we were able to differentiate all the vowels, and currently we have reached to a stage where you can differentiate the sentences people are speaking. And the idea here is that when I'm talking to you, your brain is not interpreting information based on what I'm saying. It is taking information from my audio, my gestures, slides, combining all those and converting it to information. So we are trying to apply same concept to future hearing aid device, that we take a multimodal information which includes audio, lip movement, gestures, fuse them all together, to control the noise threshold so that we can reduce the cocktail effect. And then these reconfigurable intelligent surfaces were being used to do, as I mentioned, to solve one of the problem, which was the current radio frequency sensing does not work in non-line of sight scenario. So we use these. The traditional way to measure someone's vital by radio frequency sensing was that the user need to be in between transmitter and receiver. And then you can measure their vitals, their activity pattern. But we have used RIS to demonstrate that it can be done in different scenarios. So these are patented results. So what we did that we measured the heart rate and breathing rate by comparing it with the ground truth, which was go vernier belt and bipolar for heart rate, bipolar sensor for heart rate, to compare the result, and there was an error of 1% only. So RIS has opened so many new areas, so I'm just showing some of the examples. And the next one was during pandemic, you have heard that everyone was saying that, oh, 5G called COVID. And you know, one of the important parameter is specific absorption rate. So we demonstrated by using RIS, this was a thorough campaign, that you can reduce the transmit power, ultimately the receive signal strength can be controlled, which will reduce the SAR. And then we have used this in another interesting scenario, which was brain-computer communication, that how we can use RIS for BCI communication. So the next one, I think I have how much time left? So I have 5 more minutes. So I'll just touch 2 more topics, which is RIS for localization and RIS for ISAC. So one of the challenge with global positioning system is that it does not work indoor, right? If you want to find way inside, if you want to do asset tracking, if you want to do any kind of smart home automation, you need localization. And indoor localization is a big challenge. So what we did is that how we can use these RIS, as you remember that these RIS can control the beam direction, they can steer the beam, they can act as a transmissive structure as well. So what we did that we used these RIS surfaces to do localization. So we did a controlled experiment, of course, in a lab scenario. So what we did that we have basically identified a region, as you can see here, and selected 9 different positions by making a grid through an experimental setup, which is being shown here by using USRPs. And this is what is interesting thing, that we were able to do the localization with an accuracy of around 20 centimeter. So last but not least is, I have talked about communication, I have talked about sensing, and now I'm going to marry both of these, which is called sensing and communication, joint sensing and communication. So advantages are immense, starting from spectrum efficiency to cost saving. But what we did was to demonstrate, I'll show you the demonstration as well. What we did that we developed a radar in our lab, and of course RIS as well, which I'll talk. But what the demo was that there were 2 users, as you can see, 2 subjects. They were performing various kind of activities. So what we did, we transmitted their video, their images, and also their vitals as well together. So at the same time, we were using the spectrum to do sensing and communication. This was the specs for our bespoke SDR-based radar platform, which we developed in X-band with a transmit power of 20 dBm and had 1 transmitter channel and 2 receiver channels. We used off-the-shelf respiration and heart rate sensors as a baseline. Because of certain project requirement, we were working in X-band, so we had to design our RIS at X-band. Of course, as I explained earlier, that you have to start from a unit cell, and then you go to a tile-based approach So our designed RIS had a great performance with theta plus minus 40 degree, and again in broadside direction greater than 20 dB. And this was the RIS, which was an advanced version with a controlled centralized circuitry with an interface being tested in the chamber, which shows the required performance. But this video is the last thing I'm presenting, and this demonstrates what we did. So this is without RIS. So as you can see, what we are trying to do here is that if you see number 4 here, you will see that there are 2 users. They are static, and this is the receive signal. You can see that there is no perturbation in the channel. And now we have 2 users moving. So we have the information for their target distance and also their vitals, and this histogram, which is the radar-based sensing, which has all the information. And this is basically what we are demonstrating, that how we can do both communication and sensing together. As I mentioned to you earlier, that this is the demo we specifically made for this conference, and it's work in progress, where we are able to show the vitals, and also we were able to show that we can do this in non-line of sight scenario as well with RIS. So I think with this, I'll stop. Thanks to all the funders, colleagues, and students, and especially Professor Muhammad Imran for the support. So I'm open to any questions. So thank you very much. Yes, I can hear. Yeah.
My perspective is from the test and measurement. So in the European standard telecommunication ETSI, for example, we use a parameter, a new one metric, to reflective EIRP. So that gives you the angle, the direction where we see the highest reflectivity. The challenge is from a setup, let's say that we have a bidirectional setup for the RIS. So you have an impinging wave that has to be in far field, and you have the reflected direction where you have to be also in far field. In terms of complexity, so what do you request, or how do you see the test and measurement? What do you need from us in the future? For example, we are currently discussing also a PhD student in my team. We are working on a monostatic approach. We are using methodologies from the radar cross sections to estimate the reflectivity, but from the same angle, impinging and reflecting. Do you see this is the approach to go, or where do you see the challenges and the future needs?
So thank you very much. So we have already contributed to ITSI standards both on RIS and ISAC. The challenges are immense. So one of the challenges I didn't present it here is that because of those near place spacing between the unit cells and RIS structures, we have interferences. And we do not know how to measure those and how to overcome those. So from test equipment side, we definitely need that, how we can do that. Which is a great challenge for this technology to go forward when it will go to the field. So I think this is one, but there are many others which we can talk, yeah.
First of all, good morning. I would like to ask about the communications use case of the RIS. Over there on your demo, we saw, I assume the receiver side were fixed places. There were at some locations where it was predetermined beforehand, and RIS basically just steers the beam towards those receivers. So I would like to ask, if RIS controller has no information beforehand of the receiver places, so is there any backhaul or like any kind of feedback to RIS? Basically, how does RIS controller would determine where it's supposed to steer the beam in that scenario?
Absolutely, excellent question. So the point is that you need to move toward any problem step by step. So that is ultimately what we are working on, that we have a controller which sense the environment and ultimately steer the beam in that direction. So that is the work we are currently doing. But whatever I have presented, it took us 6 years to reach to this stage. So ultimately, that is what we are doing, and that is when the real essence of race will come into play. There's one question first row. Yeah, please,
yes.
go ahead. I can hear. Okay, yeah, sure.
Thank you for the presentation. Maybe I missed that part. Sorry for I was a bit late. For the communication scenario, as academics, we love working on IRS because lots of optimization problem. It's a good. But I have an operational perspective question. These surfaces are not frequency selective. That means that, for a 5G band in Turkey, we have 3 operators. If it's good for one operator, it means interference for the other ones.
Indeed.
Who will control these resurfaces? So we are talking about the inter-operator centralized control mechanism. So how do you see the future for the implementation in the communication sense?
I think that is a very valid problem which we get as well. But the solution to that is this standardization. So that needs to work on to solve this problem. And this is what we are working in ITSI. In 3GPP, they have started for RIS as well. And that is the key which will bring everything together, because I know it's not possible to put 3 RIS for 3 operators. It does not make sense. So the answer to that is that standardization stages have been started, and ultimately we will have a standard which needs to be used in future.
Thank you.
Okay, so we actually work with Qammer. Our first project was in vivo communications. So we just wanted to develop a network inside our body. And, I still remember those days. Actually, they did some tests with some of my graduate students with the real bodies.
Dead bodies, yeah.
Dead bodies. But anyways, Qammer, when do you plan to put wrist inside the body? So, do we need that?
Probably on the surface of the body, definitely
Surface,
we need.
not inside.
Yeah. No, not inside, yeah.
Okay. All right,
communicate
so
inside,
let's thank our speaker, my good friend, dear
Thank
friend Qammer, for this wonderful talk.
Thank you. Thank you for listening. Oh. Yeah, thank you.
We would like to thank to the dear Professor Dr. Qammer Abbasi. And now we are inviting Professor Hüseyin Arslan to the stage to present his gift. Okay. Now, to introduce our keynote, I invite University of Leeds Associate Professor Dr. Syed Zaidi.
Okay, let me start from here, and I'll see if I can stand at one place. I'm pretty bad at, staying stationary. First of all, my apologies for this morning. I think those of you who came early morning to hear about AI ended up hearing about RIS, which I'm really grateful to my friend Qammer, who stepped in. I was stuck in Istanbul traffic, so couldn't make it at 8:45. So hopefully, I mean, today I cannot cover all the aspects. I think, generally a straw poll, what would you like to hear about most, theory or practical stuff which is happening in 6G? Because I think you have heard quite a lot about system level stuff, right? And I'm like a typical theory guy who is stepping into systems world. So basically, I do bit of both theory as well as systems. But today I'm mainly focusing on, from 6G perspective, what system level issues exist, where are the sort of, we see hype about certain things in the community, and what is the reality beyond that hype? I mean, are there areas where we should be focusing quite a lot, or are there areas where we shouldn't be focusing that much, which can be a bit controversial as well. So please, this is more or less, I was asked by WWRF a couple of weeks ago to talk about what 3GPP shouldn't be doing. So this comes from that perspective, that if we were to scratch a few things and start fresh, what we should be looking at, and then trying to decipher some of the keywords which you hear, like AI native, cloud native, what do they actually mean, basically. So I'm based at University of Leeds. I co-lead one of the 3 future technologies hub, future comms hubs in UK. So these are similar to 6G hubs in Germany, or 6G hub in Finland, 6G flagship. Basically, you will hear from them later. So I co-lead it with Professor Muhammad Imran, who spoke yesterday, with dear friend Qammer. He's also part of our consortium. Then we have few other colleagues. So we are pretty much geographically spread with 6 universities. Hamid is part of that as well, so he will talk about a bit of ORAN as well after my talk. So in terms of Cheddar's current focus, we have 3 pillars at the moment. So the first pillar is emergent systems, second pillar is around sustainable systems, and third pillar is human-centric aspects. And we look at a variety of sort of research topics underneath each pillar. So for example, pillar 1, we have integration of MEC with ORAN ecosystem. We look at how we can autonomously distribute AI across the whole cloud-native ecosystem. We are looking at how we can automate generation of apps like X apps and R apps for ORAN scenarios. And then we are looking at things like how do you basically optimize network to support digital twins and digital twins of networks itself as well. And then lastly, we are looking at foundation models for telecoms as well. Within sort of pillar 2, we look at carbon neutrality, so mainly sustainability aspects, how we can build future generation of communication which has sustainability augmented by design. And then we look at ISAC as example. Qammer was mentioning that the network itself can use ISAC to optimize the performance, for example. So we look at those sort of aspects. Then we look at things like green auto ML. So how do you orchestrate machine learning pipelines to be green as well? So I'm not going to talk about all these pillars today. These are within third pillar, we look at privacy and security. Like when we talk about ISAC, one of the fundamental questions which people will ask you is that how do you deal with privacy, for example? So all those things are explored within pillar 3 and security aspects as well. Okay, so I'm not going to talk about this. These are the key research areas we are focused on. We have few experimental sites deployed across Leeds, across different use cases. We are also part of AI-RAN Alliance, as is my friend Hamid as well, as he told me yesterday. And we are trying to contribute towards development of AI standards for networks, especially RAN, through this initiative. So, so far we have heard about 6G and various different visions. You guys must have seen this famous HexX2 vision, which sort of gives this flavor of 6G being, all about creating virtual replicas of physical world, so creating digital twinning, pairing the digital world and the physical world together in a human-centric way, so that you can enable all these sort of applications. So I will not spend too much time here. You have seen this as well yesterday from lots of speakers which presented this IMT 2030 framework, which started from this triangle of URLLC, EMBB, and MMTC, and expanded it into hexagon. It's 6G, so we need to do 6 things, right? So it has gone to 6 things, and it's become hexagon, which includes ISAC, ubiquitous connectivity, and AI itself. I'm not sure whether this diagram is really clear, but you can see the problem this hexagon solves is that in 5G, we had certain use cases which fall between these 3 traffic classes, like RATCAP, for example, or robotic scenarios which require EMBB, but also URLLC. So those can be now more effectively captured by 6G traffic classes, basically. Okay, so the other aspect, this is a very technology-driven view. So whenever I speak about 6G, maybe I should try and move if I can. Yeah. So now I don't need to stay here. Okay. So whenever I talk about 6G, one of the things which we discuss is that this is very technology-centric view. What will happen with the 6G? And I think Eric did a fantastic job of sort of grounding us a little bit yesterday. We need to look at things like this sort of analysis. Past analysis basically looks at what is happening in political sphere, what is happening in economic sphere, and what are the societal factors, and what are the technological factors. And I think a lot of 6G research questions will come from contrasting these factors, basically. So for example, one of the things we can talk about is sustainability. So at the moment, operators spend about 19 billion a year spending in energy bills for networks, for example. So about 40% of the operational expense is from energy consumption, for example. So when we talk about native integration of AI, and somebody already raised it, AI is good to tame the complexity and automate through automation, but that brings in additional cost for energy consumption, right? So when you're training models, it's not free. That consumes energy. So with each generation, what we have noticed is that at a sort of a technology level, the energy consumption has decreased, but with each generation, the overall energy consumption has grown up, right? So when we talk about 5G, it's consume more energy than 4G, for example. So if we continue this trend for 6G and we consume more energy than 5G, for example, that doesn't fit with this societal need for sustainability, and it also increases the operational expenses for operators as well. So how do we solve this issue of automating a very complex ecosystem, which we have made complex because we wanted flexibility to serve various different use cases, while also enable these sort of native integration of AI to tame this complexity, at the same time attain energy efficiency. We want things like metaverse and all those sort of things running on 6G network, but again, we also want to have privacy, so we want to have a location-centric services, but while preserving the privacy. So all these factors, if I pick any of these 2 factors and contrast them, I have a research problem to solve, basically. So I see that, in 6G, rather than solving something really, fundamentally different, what we'll end up is solving issues which 5G already has, and we have sort of, these sort of spheres dictating where things should go. Like vendor lock-in, for example, is a big issue, and Open RAN tries to break it in. But Open RAN has sort of suffered from the fact that the interoperability between components is not mature, the testing is not there, and the testing is complex. Who writes test cases? Nobody has money, lots of OTEX, all that. So, last week we were discussing this in NTIA event. So I can talk about this for, another 10, 15 minutes issues about Open RAN, but I will quickly delve into what we believe will happen in 6G for sure. So one thing is for sure, we will continue with this trend of disaggregating and virtualizing the resources. So we are moving more and more towards cloud native implementation, which is for sure. With this virtualization and cloud native implementation, we have more flexibility to implement various different services. From our perspective, we think that, this is again a personal take on 6G, there are a few things which we should definitely have within the 6G ecosystem. One of these things is semantic awareness. Now, when I talk about semantic awareness, I do not mean semantic communication, okay? Here I mean semantic awareness, so contextual awareness of when using AI, for example. So when you have AI embedded in the network, you want to learn once and then reuse this knowledge across different scenarios while using this contextual knowledge as well. So if I have trained my model somewhere in a busy city scenario, then this should also work in other places in the similar sort of scenario. So I do not only want to learn, but I also want to capture that context so that I can reuse or transfer my knowledge across different scenarios. I also want to do something like, if I have learned how to slice a resource in the network, I have also learned how to slice a spectrum for different demands. So the semantic structure of the problem is same, although the AI is applied at two different places, for example. So with semantic awareness, I mean that we need to move towards semantic aware AI and semantic aware networking itself. We need to have something done at device side as well. So one of the fundamental issues which happened with 5G was that there were no devices. I mean, release 16 modems are just in the market, right? So you don't get release 18 modems manufactured by Qualcomm. So, and for each release, when their new features are rolled out, you need to redevelop the firmware which runs over it, right? So the whole onboarding mechanisms change. So what we need to do is learn from automotive industry and try to abstract this complexity. So on device side, innovation is sort of independent, much more like Open Run. So can we write apps which run on hardware abstraction layer and then simplify our life on device side as well? Okay, so today I'll just focus on AI native. I will not cover all the aspects which I sort of showed you in the last slide. With AI native, different people have come up with different implementation. You might have seen this from Ericsson, for example, showing various different ways of integrating AI in the network. So they talk about you can have models which are specific to each layer, but you can also have sort of augmentation of all these models to do the entire protocol stack as a single AI model. And you saw this diagram yesterday as well in one of the presentations, which sort of showed you that each layer had a machine learning model, and then it sort of merged into a large machine learning model. So what I want to explore today in a few minutes is what is the interplay between AI native and cloud native, basically. From Nokia's perspective, I'll pick this definition. Nokia has a very good white paper on this. They talk about empowering radios with AI ML so they can tailor signaling schemes, protocols to achieve best performance in any given scenario, not constrained by predetermined selection of predetermined parameters. Again, with AI native, you can apply this. I mean, I'm particularly focusing on protocols and signaling, but you can apply AI native to sort of AI native air interface, or you can apply it to intent-driven networking, or you can talk about cognitive closed loop control for infrastructure as a code, or configuration as a code if you are in SDN domain. You can talk about Isaac, for example, with AI. So all these are sort of integration of AI native aspect. But the fundamental problem we have here is that we want AI to be embedded in the RAN in a way that it allows us to select the best possible configuration of the RAN, right? Now, this is an inverse optimization problem. It's not an optimization problem. Typically, what neural network does, it takes some inputs, right? So you provide certain inputs as a feature of a neural network, and it will give you an output, which, let's take X as an input, which is all your control knobs. Then Y is your KPI, right? So you'll get a certain throughput if you put all these control knobs, and that allows you to optimize the network, for example. But what you want is reverse of it. You want to specify a KPI, and you want to get optimal setting of these control knobs, right? So it's an inverse optimization problem. It's not an optimization problem, right? And you cannot do this unless your neural network has seen those scenarios, right? So nothing magical happens if you do not train these neural networks on huge amount of data, or at least on the data which is representative, basically. So the inputs need to have a distribution which is representative of those cases which neural network hasn't seen, basically. So trying to generalize this over, this sort of definition of, having sort of optimal configuration by magic doesn't happen. So we need to think about this, that how do we train our models so that they can allow us to do this sort of generalization. Now there is a focus on, these models need to be generalized over environment. So it doesn't matter if I run this in Turkey or somewhere else, as long as my model is trained, I can deploy it somewhere, at different places. So this is what they solicit. RAN intent, I do not want to optimize one thing at a time. I want to optimize throughput, I want to optimize energy efficiency as well. So I'm selecting solutions which are on Pareto optimal frontier, right? And then RAN tasks, I want to generalize across different traffic classes as well. So it's a very complex problem. And again, from AI native air interface perspective, you have seen this yesterday as well, which was mentioned that we are looking at things like neural transceivers. So in terms of AI native air interface, people are now talking about sort of augmenting this secondary knowledge into the transceiver. So I said that, you can't do magic without adding anything additional in the transceiver, right? So here you can see an example. You are adding ray tracing information, for example, to generalize that neural network model. You are adding specification knowledge for propagation models, for example. So if you add those sort of things inside, your AI native PHY implementation, you can do a bit better. And here the question is that, can we obtain generalization through adaptability? What it means is that, do we take one neural network, train it over huge data, that gives a good performance, or do we apply neural networks which can learn in field and do site-specific optimization? So this is already going towards the concept of digital twin, right? So you can see where we are progressing. That if we can have a network's digital twin, or at least for propagation here, we can do quite a lot better for generalization. But after doing this, what do we get? We get this. We get about a couple of dB gain, specifically if we consider the inferencing latency, because this is running on GPU, right? So you're running a neural network model on a receiver, on a GPU, you get 2 dB gain if you put a constraint of 10 microsecond latency. And that 2 dB gain costs you quite a lot, right? So that's where we are at the moment. So we need to think about, do we need AI in everything, right? I mean, that's a fundamental question. Okay, obviously I'm not saying this is not an interesting and promising area. Obviously there needs to be more research in this area. But we need to be realistic about what do we gain and at what cost, basically. If we are gaining 2 dB, maybe we can do certain optimization of a model-based approach, basically, which gives us similar sort of performance, basically. What it allows us to do, though, is that these transceivers can now be virtualized, right? So they can be deployed as containers on the top of your general purpose infrastructure like GPUs. So this allows you to open up the cloud native approach, whereby I can deploy new models, do lifecycle management, update them on the fly, so I can always optimize my network. So I invest in infrastructure once, but I keep evolving it rather than changing infrastructure every time. I'm not sure how much time do I have, but just give me some indication how I'm doing with it. So in terms of Open RAN, again, you will hear from Hamid quite a bit, so I will not delve into that. But there are lots of interfaces which allow you to implement AI. We look at various different use cases of Open RAN, how we integrate edge native applications and what are the features of edge native. I will skip it in the interest of time. But as I said, that one of the ways of generalizing or solving this inverse optimization problem is by introducing digital twins. And you do not only need digital twins for optimizing your machine learning model, but you also need it for observability, because you need to know in the network what is happening where, basically. Lots of different ways of implementing digital twins. You can have this classical PGM-based approach, which you can adopt for implementing digital twins. Or you can sort of approach it from large language models perspective as well. Again, I'm not big advocate of implementing AI directly into the network, because that sort of ends up deteriorating user experience. You can't be experimenting in live network, right? So you need some sandbox environment to do that. I'll not talk about digital twin in detail, but I mean the architecture we are soliciting is of this sort of nature that you define your performance optimization in terms of intent, and then you have a network digital twin where you basically learn and develop XApps, RApps for optimization, which you deploy in actual run, and you monitor how the performance evolves over time. Okay, so I will just talk about how XApps you can automatically generate. I mean, there are lots of different approaches of automating this workflow as well. So you can do it using things like TinyML, for example, where you train offline and then deploy, or you can do retrieval augmented generation using LLMs, for example. Since we are running all this on GPUs, we can run LLM alongside L1, L2 implementation. So that's the advantage of having AI native implementation. Last few minutes, I would talk about multimodal LLMs, basically on the edge. These are not just for optimization of edge itself, but also as a use case interesting. So we are developing some models of how we deploy these multimodal LLMs within private 5G infrastructure. Again, we are looking at things like if we can specify intent in a high-level way, like here in aerial VLN, for example, you only specify the mission and you let the robotic platform choose how it carries out mission by defining low-level functions. Then can you orchestrate this autonomously, and can you do this for the RAN itself as well? So the framework behind this is called REACT, which is based on reasoning and acting. So you have two aspects. You use LLM to reason, and you also use LLM to act. I will not go into the details of React framework here, but you basically define agents, which was mentioned by Dr. Van Tong yesterday for optimizing each aspect of the network. These agents have various different elements, which include memory, tool set, which they can use, self-criticism, chain of thoughts, tree of thoughts type of approaches. And then from this perspective, there are certain performance criterions you need to care about, like energy consumption, latency, etc. You define certain tool sets. Here, I'll show you just example of one implementation which we have done. So this is for UAV-based coverage. And what we are using is that we just specify this intent for an agent and specify the goal it tries to achieve. We train it over aerial images. And here, what it does is it autonomously tracks the user, basically, and positions itself in an optimal way to optimize the coverage. So you can see here that coverage rate improves quite a bit. Okay, so by doing these sort of agents, we sort of have this cloud-native implementation. Again, with cloud-native, you can do this whole lifecycle management very easily. So let me just conclude. I will not go into lots of different things. I will just conclude by these proposed design principles for 6G, which are evolving. I think if you read Hexax2's documentation, you will see these principles. You can already see that for 5G, we had lots of options. We are trying to converge on one option for 6G, so we don't have many design choices. AI native, but intelligently, AI doesn't make sense everywhere, basically, so we need to think about that. Integration of edge, basically, and then simplify the architecture. We need to learn quite a lot from IT industry. That's a key message. So we are still sort of specifying these edge interfaces. In IT, WASM already exists, provides edge services as well. So we can easily deploy that. We need to look at where things make sense in terms of doing. For example, latency optimization can happen in DApps. It can happen in eBPF running in the lower layer architecture, or it can happen in XApp. But not everything requires eBPF program running in a kernel, for example, and not everything requires XApp, for example. So we need. I will conclude by saying we need to look at this IT industry. We are always chasing IT, right? Because telecom is providing services for IT, basically. So what has happened classically is that they have gone and done things, and then we have built networks to service them. We see this PWA architecture where service worker and caching exists. We talked about caching for ages, never implemented it in practice. We talk about joint communication and sensing. you see these applications where they track your movements and how you use the application. So some sort of application, at application layer, this concept exists. We talk about edge application layer, this exists as well. So we need to simplify architecture, reduce, think about where things make sense, let application handle those things which should be handled by application, and not try to build those into network stack. So that's the key takeaway, I would say. Thank you. Thanks a lot.
Well, I think you have a lot of slides that you skipped.
Yes.
We need to invite you one day, I guess, for a longer tutorial or something like that. We can take a few questions. Any question? Yes, I'm all right.
Many things like
No, he already asked that.
okay, so many things. I think not try to standardize, over-standardize. So I mean, a lot of things end up in specification, right? Never get implemented. Then we have variety of specification. Like you have SCTP over IP between, CU, CP, and then CU UP has, basically UDP over IP. I mean, why two things? Do one thing, properly. So I mean, there are lots of, and there is already talk by, for example, Qualcomm guys to simplify the core. So some of it can be moved over IP, for example, because PDCP and RRC specifications have grown over the time with endless features which never get implemented, right? So, I mean, all those kind of things can be simplified in 3GPP specifications, but I'm not sure whether that will happen.
I think in this conference, if you learn one thing very clearly, the standards are now very fat, I guess. We put pretty much everything into the standard, but I don't know, whether we are using 50% of it or maybe less, right? Any further questions? Okay, all right. If not, then we will thank our speaker one more time. We have a gift for you as well. Where is the gift?
Qammer has taken.
Qammer,
has
did you
taken.
take the gift? Okay, well, we'll do it with the next one. Did you forget about it? All right. Anyways, we'll do it next time with Ahmed. So together. Another thing, actually, I don't know whether you had the chance to talk to, other companies who are manufacturing products. If you had that chance, probably one thing that's very clear is that these newcomers, new babies, who are trying to integrate into the system are having very difficult time. One of those is ULAC, actually. We have representatives from ULAC. They are building base stations, core networks as well. But like 4.5G LTE advanced, one of the difficulties they are experiencing, I was also the founding chair of the ULAC, board actually chair of the ULAC. So one of the difficulties we had is how do we get into the market? Even if you have better product, cheaper, it's not easy. One reason for that is because the market is already occupied with the vendors who have been there for a long period of time, but even like starting from 2G, 3G. All these standards are not completely independent of the previous standards. So, we built one new standard on the top of the previous standard. So if somebody came into the market earlier, like Huawei, Ericsson, Nokia, then replacing them is almost impossible. For example, ZTE, you heard about ZTE yesterday. Even, they have great products, but even they are having hard time to enter Turkish market. Turkish market is 80% Huawei, 20% is Ericsson and Nokia. So if anybody wants to get into the market, it's very difficult. And the reason for that difficulty is because compatibility and interoperability. So even for those companies that we divide our market is, they take the whole region, not even a neighborhood, not even a city, the whole region, like the Marmara region or Aegean part of like half of the Turkey or the other half of the Turkey. So speaking of that, now there is a new technology that Ahmed is gonna, I'm kind of like preparing the groundwork for him. He will talk about more details. He's a very dear and near friend of mine. We are also collaborating with him. And this Open RAN technology is a must now, especially for these new companies and to advance the competition, in this area. And to me, if you ask me, what is the most critical thing, in the future is basically Open RAN. So that if better antenna can be produced by a company, we have to be able to integrate it into our system, or RRU, we have to be able to integrate it into our system. Anyways, so I would like to let Ahmed, my good friend, take the floor and discuss about Open RAN for the next 40 minutes. There was a panel yesterday as well. Maybe, Ahmed, you can also summarize. And our president of BTK is basically, like in every country, they have regulators, right? In US, it's FCC. In UK, Ofcom, right? So in Turkey, it's BTK. So they have the power of everything. So they control the spectrum and, control the operators. So I'd like to welcome our president. Welcome. Do you want to say a few things?
Thank you. Sorry about that. He's here. I'd like to welcome you all, first of all, to this great conference. As we all know, we were talking about 5G maybe a year ago, but actually, Mr. Professor Hussein, he's the one who started the 6G event in 2017. So actually it's a matter of focusing, and we all have seen that we were talking about 2G, 3G, 4G, and now 5G will be implementing it maybe in a year or so. And then, of course, we'll be going ahead with the 6G. With every generation of this communication, actually, we're trying to achieve the goals that are set ahead. So autonomous driving and maybe robots and so on. So dark factories, maybe, in the future. So it's all going to come. But it's all step by step. And every innovation that we make in the field is going to contribute to this new generations of communication technology. Thank you.
Thank you very much. So it was kind of like not planned, prepared, but I'm very happy for the president to visit us. It's an honor for us. So my friend is going to talk about Open RAN. Probably it's going to be also an important thing for the regulators to have this Open RAN. Right, Ahmed? Maybe you can talk about that as well. Anyways, so I'd like to let you.
Thank you very much.
Just talk about.
Thank you. Thank you. Okay, thank you everybody. Thank you, Professor Arsalan, for inviting me here, and it's great. It's a great honor to have such fantastic guests here, from the president of the regulator to dear guests from everywhere in the world. So, just I start with a quick introduction about Open RAN and the projects that we have, our team. And then I'll carry on with a little bit more about machine learning. But basically the parts that I'm going to cover in this talk is the pains and gains of Open RAN from an implementation type of perspective. So just to, in a way, carry on what Professor Arsalan mentioned here, is that Open RAN gives us very good opportunities to carry on the work that we are doing in smaller businesses, and enables smaller players to get into the market, a market that is now dominated with big players. That is potentially one of the big reasons that the governments are investing in this technology, because they can help their SMEs to grow, and in a way the competition is formed that way. So, all right, let me go inside the slides, and I'll cover those aspects one by one when we reach to the relevant part. So, a quick introduction about my team. A lot of this work that I'm going to present is the fantastic work of these nice group of people, and the funders of the projects that we have. So we are basically we call ourselves iTwins Lab, so we are doing the work, intelligent telecommunication, the wireless telecoms for society, actually. So that is one of the key things that we want to look is, we want to be good for the society, and it goes with the main concept of the University of York, which is the brands itself as a university for public good. In our group, we have three main Open RAN projects. And one of them, YORAN, is the Yorkshire Open RAN, which is a flagship UK Open RAN project. It's funded by the government of the UK, and it has operators involved like BT and AQL, which AQL is a smaller operator, is a regional operator, and there are a few SMEs, as Hossein Oja mentioned, that there are small radio manufacturers, SMEs, that they can build RUs, but they cannot easily compete with the bigger manufacturers and get into the market. In this project, we go from the RU to the network to RIC, and we have two SMEs based in Yorkshire, in Shipley, a small village, but they built very nice RUs for the neutral host small cells. And they are being tested in this project that we are doing. So very, very supportive of the local industry and helping the other companies to get on board. We also have another software company, another SME called Jet Software Engineering, and this group is also working on development of DUs and XApps. So again, another software company can get into the market. Reach is a project that is working with the Blackpool Council, and we are going up to the deployment of the commercial RUs with the open software, and we are going to test it in busy scenarios. I'll talk about this later. ORAN Twin is a project that we are with Ali involved, so funded by EPSRC. There are other projects that I mentioned, just AI for good and for the society, is that we are helping with our digital platforms, the communities, the remote communities in Vietnam. We have air pollution monitoring works with Hossein Oja and Berk Oja in Istanbul, Royal Society one. And we also look at the ethical aspects of AI in collaboration with University of Auckland in New Zealand. So loads of activities around that. Now let me focus on Open RAN. Open RAN, basically, we have the motivation here is that the current landscape of the radio environment, or the RAN basically, is vendor locked. As mentioned, all come as a package. Customization is done within the boundaries, so you're not flexible to do whatever you want. it's within the boundaries that defined by the vendors. So vendors can tell you, okay, we have this, we have that, and let's do it. If you want something beyond it, it's not necessarily possible. So innovation is also vendor controlled. So if, let me actually, I think it's well, can you hear me? Yes. So innovation is vendor controlled. So if vendors decide to do innovation in AI, you will do the AI. I mean, those who have worked on cognitive radio knew that how difficult it was for us to get the data, to get the algorithms that we implement into the network. But Open RAN is going to help us with that in a way. So smaller players couldn't get in, especially on the software side, and limited data access were stuff that we had. I'm aware of the time also. So there is another need on the market side. So by 2024, Open RAN market is still very small. It's fairly tiny compared to 4G market, compared to 5G market. But you know that governments are investing in this technology, especially from the aspect of that they support their local industries. So there is a push for that. The push is that by 2030, in the UK, 30% of the traffic must be Open RAN. So this is something that is defined by them. And we believe, or our estimation, so this is a commercial analysis that a postdoc of mine has done, who is working on the, well, innovation or commercialization project. So more than 27% is going to be, 37% is going to be Open RAN. So Open RAN is going to claim a bigger chunk of the market in these cases. So this is a big market. We need to start working on it, but we are all talking about Open RAN. What is Open RAN? Yesterday, I think it was the director of one of the companies, if I'm not mistaken, Dr. Yatim, Mehmet Yatim, he was mentioning about the benefits of Open RAN from a veneer side, and they were all very, very correct. So Open RAN has a series of very good inventions that, or innovations that we can call, that enable the whole system to become better. So it introduced disaggregation. So we have ORU, which is the Open Radio Unit, ODU, Open Distributed Unit, OCU, Open Centralized Unit, and this disaggregation enabled to different parties contribute to each smaller part. So you don't need to build the biggest base station. You can only work on a smaller part of it. So if you have a smaller R&D, smaller development side, you are basically easier or better positioned in the part that you are working. Then there is a new component that is added. It's called RAN Intelligent Controller. As you can possibly see, there are two parts of that RAN Intelligent Controller. There is non-real-time RIC, and there is near real-time RIC in the architecture of ORAN. And I'll talk about these two a little bit later, because they are the place that the AI is happening in Open RAN. But virtualization and open interfaces are also a big part of that. Virtualization, as Ali previously perfectly mentioned, it enabled the cloud part of the work with softwareization. So it is an important part that enabled a lot of these. But it has been a little bit there. With NFV, SDN, we had it. So, but open interfaces are another key invention that we have here. You see these nodes that are E2 nodes or A1. These interfaces enable that different parties, different parts of this Open RAN architecture work together, work with each other, and pass the messages to each other. looking at this design and having all these key inventions and motivations and the nice things that we have about Open RAN, of course there are coming issues with that, which has not been mentioned yet. The challenges are becoming two major things: interoperability and integration. So when we say interoperability, I actually later on when I go to the integration part, I'll give detailed examples. But it is fantastic if you have an RU built by an SME and a DU by a software company, a CU by another company, and they work together perfectly. This is in the best word, but this is not happening. It's not that easy. That's why we had all those vendor locked and all those systems, because they were working perfectly together. And they were efficient, they were optimized for each other. Now, you have one company that has their CU or their DU, and they release an update. Actually, we have seen this in recent days. They release an update, it stops working with some of the RUs that you have. And the same happens for the RIC and the other parts of the network. So it is very challenging to make these parts to work together and integrate them as a big system. So these are the challenges. These are the challenges here. So let's go a little bit more detail and have a look at the RIC. So we have two RICs. And inside them, we have different components. So we have on the top of this figure, actually, I have the near real-time RIC, where we have third-party applications nested there, or can be nested there, called XApps. There you can see other parts that are other components that are within the architecture of the RIC. There is AI/ML support, there is conflict mitigation, there is security unit, and there are two other important parts: data shared layer and database. Similarly, in the non-real-time RIC, which is in the bottom part, it is the non-real-time RIC is actually placed in SMO, which is the basically a part of the type of new architecture that is proposed by the Open RAN, by ORAN Alliance, but it's something that has been there. So orchestration has always been there in a way. Anyways, again, in dark green there you can see that we have the AI/ML workflow again, and we have some data management part, and we have other third-party, basically, applications called RApps. So the difference of these two RICs is that the first RIC, which we call it the near real-time RIC, it works basically in the scale of hundreds of milliseconds, and the non-real-time RIC is about a second. So you see that it's getting closer to real-time, but the parts that are more policy-oriented, the parts that are less close to the real-time are the ones that we are using them in the non-real-time RIC. The challenge that I have, or the challenge that we have a lot, is basically this part. There is AI/ML support, there is AI/ML workflow here, and as you can see, there is something very nice that Professor Hussain mentioned just before, that sometimes we over-standardize. ORAN Alliance let us be free to choose the way that we do the machine learning in ORAN. So if you can see, they are having 5 or 6 ways of actually implementing machine learning at different locations in the network, in the RIC basically. So you can have model training somewhere in non-real-time RIC, and the inference at the near real-time RIC. You can have both of them at non-real-time RIC. You have some part of it at near real-time, non-real-time. But the challenge that here is coming that if you write an XApp that requires the machine learning, for example, from near real-time RIC, and you use a RIC, for example, OSC RIC, or from one vendor, from one software vendor, basically that RIC may not have that functionality there embedded. So you have to tune your XApps. You have to tune your XApps based on exactly what your RIC provides, which is again becoming a challenge in interoperability. You write one XApp for one RIC, you write another XApp for another RIC. So this is not working well. This is a challenge. So necessarily, if you want, I mean, it's a very wide example, but it's like that you're writing an app for Android and an app for Apple phones. The difference is basically tiny. The core functionalities are inside. The wrapping around it is different. But if these are implemented differently, you can't do that. So what is the solution? So the detail of this is in this paper that we published just recently, but what is the solution? The solution that we propose is this, and this is one of the contributions of my group and being published in a conference, in the standardization conference actually, as a suggestion. So we provide something that we call it an AI engine. So this AI engine is like that you are taking your intelligence with yourself. We are providing XApps that are working as an AI engine. So then other XApps that you are writing and you are going to work with that is actually a second XApp that can run on your system. So for example, you want to install a network slicing or energy efficiency XApp. You install the AI engine first and then energy efficiency XApp of yours. So this basically helps you to not be dependent on what is provided by the RIC, but also it is your own system that you are taking. Now it becomes like Android and Apple. So you have only to change the outers of your programming. The inside core is the same because you have your system taken with yourself there. So in this system, if you can have a look, we are having the model training in the part, and we have this data pipeline. One important thing is that in near real-time RIC architecture, we have this data shared layer and databases. Actually, many of the RICs, whenever you are going to talk to the providers, the simplest and the first XApp is that, oh, magic, we can get the data from the network for you. And that's an easy type of action that you can do. It's not the Hello World XApp, but it's not a very complex XApp. So you can get a lot of information, a lot of KPMs from the network here. So that is why it helps the machine learning actually fairly easy, because you can get the data from the network. And again, you are not vendor locked. So that is the part that helps the machine learning. And as you can see, we have components that basically send the train model to the client XApps and also getting the data from the data shared layer and the database. So what we can do, what are the applications? What are the applications of this? So we have different use cases that we can use. One of the most common and interesting applications are the energy saving. The other one is the network slicing, and localization is another one. Interestingly, when we are talking about energy saving, we think that all the use cases could be similar. You just reduce the transmit power, or you just put some of the RUs to the sleep mode. But the matter is that the way that you design your XApp, the way that you do the intelligence is different. If you have an HDD scenario, which is the high dense network, to a factory, these are different. I told you earlier about a project that we are doing. It's called the REACH project. In that project, actually, we are looking at the city of Blackpool, well, small town, but those who are in the UK and follow the TV programs in the UK, they know that it's a very party-like a city in the north. And there are loads of shows like Air Show, and there is Strictly Come Dancing, loads of type of weekend type activities, and it is making that city very busy. But at the same time, during the weekdays or at nights, loads of RUs are going to be unused, so because there's no one there. We keep the coverage, but still do the energy saving. So that is one of the use cases. The other one is a smart factory, which is the Advanced Manufacturing Research Council-like type of it, or factory. This is the part where we do the smart factory energy saving, a little bit different. And the third use case is the controlling a robotic dog in the URLLC type of approach, and from far away. Each one of them have their own challenges and features, but what I'm going to show you is the dense scenario. We are going to cover these parts. We are going to cover this part. This is the places on the map that they are basically, we know that the base stations can be there. And we have different use cases. Also, public safety network is a use case there. And we are having neutral hosts because we have multiple operators that they want to use these, and they can share these dense network with each other. And we are having basically the presentation. We have different partners here. The Blackpool Council is there. VMO2 is there, AQL, and of course the University of York. With SafeNetics, we also check the security of the whole thing. So this is the general structure. Now we simulated this first in a RAN emulator where we have this number of cells. They are basically 12 cells, and we have 50 UEs in different locations. We use 2 bands because there are multi-band RUs going to be planned for this, using N77 and N78. And each RU can have 2 radio cards. The beauty of this new design is that each RU can turn on or turn off one radio card, but the electronics behind the RU can stay basically alive so that the network can discover that. So it's network discoverable. It's a type of deep sleep mode. So the energy consumption is going to be far lower. So we are going to place our XApps here and show you how this system works. A few other parameters about this is the KPMs that we are getting. So one of the market leads is Viave in emulation of the network. So we use some of the parameters that are provided by Viave. Some of them are basically general, the KPMs that are 3GPP defined. But Viave have some extra KPMs that they can be defined in the further 3GPP standardization, or we can use it from particular RUs that we request. So some RUs are still capable of providing this information to us. So that's why we wrote 2 XApps differently using different technologies. So for the sake of time, I'm just passing by this. So this is how the workflow of the part. So we have the energy saving XApp and also AI engine. So getting the data, requesting it, and then training at this point, and then sending the trained, here is this, and then training is inside the AI engine, and then sending the trained model to the energy saving XApp. as you can see, this is actually one of the unique features of the system that we have at York. And it's a software called Rig Tester and RAN Emulator by Viavi. We can test XApps without having a particular rig. So we can firstly test the internal parts of an XApp and then implement it for a particular rig and check the performance of that. I'm passing this. I just want to see if I can play this video. Maybe next slide. Yeah.
So next we will be showing the energy saving XApp with 50 UEs. The 50 UEs are randomly distributed around this area and are connected to N77 and N78. As can be seen here on the top right-hand side, we have our cells and each with its own power consumption. And of course, the power consumption here is assumes that all the cells here are active, and some of them can be serving like a large number of users, while, for example, this one is actually at the moment not serving any users, but it's still in active mode. And next, we will be initiating our energy saving XApp. And as we can see, so first we are switching off cell 3. So cell 3 is actually 1. And the 5 volts here is basically to keep it in sleep mode, not to turn it off entirely. And here we are receiving the confirmation message that the action is passing to the rig tester. Okay. So as we can see, this actually shows the total power consumption in the network, and it's like for the case of 50 UEs, we're able to reach around like 10%.
So I stopped this video because of the time. So it shows that how the XApp is written and how it is implemented. So this is basically, and then we have our results. So it shows that how different XApps can work. Sometimes you can have more machine learning applications. Sometimes, I mean, a simpler heuristic can work for you in different scenarios, depends on the complexity of your scenario. Again, this is a work that has been published in WinCom in Leeds, in an IEEE conference in Leeds, and actually we won the Best Paper Award. So we have the beauty of that, which shows that this work has achieved some nice community level appreciation. So the next thing that I want to talk about is the work of a colleague of mine, Professor Alistair Bear, and that's cell-free massive MIMO. So cell-free till now has been a very academic concept, but with the help of ORAN, we can actually bring this into more reality. So this is the way that basically the concept is that a user can be supported by multiple RUs, and the cell edge users won't exist anymore. All of the users are basically supported by multiple cells at multiple RUs or base stations at a time. So it's a type of extension of similar to Compact, type of extension of that with loads of antennas that are distributed. So in the ORAN context, actually that can happen much better because there we can have DUs that control multiple RUs. So it's in terms of synchronization, it's going to create improvements, and it's perfectly achievable type of scalable work, because with the traditional systems, if we want to implement this, we are going to have issues with the scalability. But with DUs controlling few RUs and having it in the ORAN context is going to be much easier. So I'll skip this. And I want to talk about the York testbed. So I talked a lot about the implementations and the challenges of Open RAN. And now I want to say about the testbed that we have. So have a look at this. In a normal scenario, you all see just one logo. It's all Huawei, all Ericsson, all Nokia, ZTE. But you see here in our basically open source version, we have FlexRig from Oran Alliance, we have SRS RAN, we as CUDU, we have RUs from Ethos Research, which are the USRPs basically. And we have also open UEs. On the commercial side, we also have here AQL, Core, ICE Wireless for DUCU and RIC, and then multiple versions of the RU, and then it works with different commercial UEs. Interestingly, these two testbeds can be mixed and matched in a way. So we tested Benetel radios with the open source testbed. So this testbed is an example, I can say it's a very good example of how Open RAN can be implemented. And it's a challenge. It's a very, very big challenge. Many of these don't work. So I mentioned that ICE Wireless just gave recently a release. It's stopped working with Huawei. And it's not working with FlexRig anymore. So we are sending them messages about their bugs, and we are trying to fix that together with them. So the integration is a big challenge, but it is an opportunity for all of these smaller players to become into the market, to be someone. And operators like AQL, which is a small IoT operator, and it's a in local areas, they can use this for their private networks. So again, yesterday we had a panel discussions about private networks. And this is one of the ways towards the private networks and towards having networks tailored to applications like, for example, smart factories. And so NTN, I think after this talk, we are going to have talks about NTN. We implemented that on NTN as well. Oh, yesterday we had Chichek's fantastic talk about NTN as well. So this is a project that we have done as an initial 4G testbed, but it expanded to become NTN ORAN. And we tried it with, this is my colleague, Professor David Grace on BBC Click, which has been covered there, that work. So we had this helicite, and we put our payload, the RUs that were USRPs, with amplifiers, and we have sent it basically 60 meters high in the sky with backhaul with a Starlink. We provided 3 kilometers of coverage. And in a place in North Yorkshire that we didn't have any coverage. So it can be used for events, for search and rescue, for loads of other applications. Yes, this is the results of the coverage. Again, this has been published in an IEEE Networks magazine paper, so you can later on have a look at it. All right, I know that I'm between you and the coffee, which is very bad. I want to showcase one of our upcoming papers. We talked a lot about sustainability, and this is basically how ORAN brings sustainability. You can have edge computing that has basically loads of renewable energy at the edge. You can have data centers using renewable energy. You can have rigs running at the places with renewable energy. Through this disaggregation and distribution, you can have embedded the way of embedding the renewables into this framework. So this hopefully comes in IEEE Communications Standards magazine sometime soon. Last but not least, digital twin. Again, we have works on digital twin, and this is how with digital twin and ORAN we can expand the work in 6G. So initially we have our working system, but we can, on digital domain, we can replicate them, we can embed the AI, and then prepare the planning. During the operation phase, we can actually check our system that is running on the digital domain and have distributed and collective intelligence for that. So here the digital twin will be an enabler. For expansion, if we want to expand to new services or to new geographical locations, digital twin is actually one of the best enablers because we have all the data that we got from the ORAN, we created the digital twin, we maintained it in real time, and there we actually start with a very nice emulation, we test it, and then we do the knowledge transfer, and we start from this phase. So we actually can close the cycle using our digital twins. So I think this is my last slide. Well, conclusions, the integration is very difficult and interoperability is a key point, but implementation is as important as the research. I know this is a little bit higher tier research, but that is another key thing that we need to know. Of course, fancy algorithms are very good, but sometimes some of the operators just don't want to spend so much energy for 0.5% performance gain. So it's better to have a balanced type of activity. Thank you very much. I also want to mention that I'm a traveler salesman, so this is our new book. If you get the time to buy it or read it from your university or industry library, that's very good. It's a nice work with a set of colleagues, and it has very nice chapters about 6G and digital twins. Thank you very much.
Okay, so I think we can have questions for about 5 minutes. Sheikh
Thank you for a very interesting talk. My question is about the terminology and this what is brought by ORAN, Open RAN. I have been working on CRAN. I mean, I started working on this disaggregated RAN, starting with CRAN. You know, like it all started 10 years ago with CRAN Cloud RAN, where our baseband processing is separated from the radio. And then we could do all the processing in a centralized manner, and this can be like an enabler for cell-free, joint transmission, comp, and this has been started 10 years ago, right? All this story, and you were there, I know. So, and now, also, in terms of energy savings, you were also very actively doing research in this topic, like we were already playing with these sleep modes, switching off access points, small cells on top of this coverage, large cells, right? I mean, sleeping off these radio units, also not new. And also machine learning algorithms. We started using them 5 years ago or something, right? Reinforcement learning for deciding on which radio unit to sleep, how deep to sleep, or playing with number of antenna elements in massive MIMO with, again, machine learning. And this has been there like around 5 to 10 years. And now ORAN, like Open RAN, like thing has started. And everything is now coming back to us as if like, okay, AI and ORAN. But AI has been there for ages, cloud has been there for ages, and what is now happening with this ORAN? I mean, what is new? You know, like I have hard time to understand this. What is new with ORAN? I mean, we have been working on this AI and this also energy savings, cloud RAN. I mean, they are all there. I mean, but just I see some terminology. Okay, RIG, X apps are apps, but all the algorithms are the same. Radio is the same. I mean, what we are playing with, all these like hardware and physical layer components are all the same. And we all change these like keywords into something else and bring it in under the frame of ORAN. And my feeling is actually implementation, I think, or this interfaces being open. And then this was all theory before, and I feel like this is now happening, right? I mean, this is my answer to the question, but I was wondering also your view, because I know you have been there when all these things were happening also, you have seen the history. So yeah, that's my...
Thank you very much, and exactly, you answered your question in the best possible way. So basically, I can say opening this to everybody, to the smaller guys, the smaller players. So I can say a story about myself. So after I finished my PhDs back in Singapore, I moved to Ireland. I've been in a big research center. But when I started my independent academic life, I was alone in a department that was no one else was doing the job that I was doing, or a couple of other people. So I didn't have access to data. I didn't have access to many fancy test beds that the other people had. And that was a challenge. Now, with basically Open RAN, it's open to general public. Of course, previously we could do the simulation, but data was a big issue. Data would be simulated as well. Now we can have access to emulators. Now we can have access to actual RAN if you have a fairly powerful computer, which most of the universities have. Most of the companies or industries have access to it nowadays. We can have our open source Open RAN using FlexRIC, which is again open source. So it's just you need to spend time to learn and implement and install all of this. But it's not a massive cost. It's open to everyone in the market, everyone there. And again, XApps are there. So if you wanted to implement a machine learning algorithm, you have to either simulate it or have it. And then it was due to the big operators or the bigger vendors to implement it and use it. And you didn't have the opportunity to show it in real time that this works. But with Open RAN, that simple algorithms that we used to have for putting the base stations to sleep, now we actually implemented them. And we saw that the RUs are going to sleep. So this is very interesting, and that's basically what makes me passionate about Open RAN, because this way we are helping the smaller guys, not only the bigger groups.
Yeah, okay, thank you. Yeah, thanks.
Do we have any further questions? Ahmed, yeah, okay, go ahead.
Thank you very much for Ahmed for the great presentation. My question is about the problem about the interoperability. You already talk about some problems when some vendors update their softwares in the networks, and then it's going to lead to some failure, right? And I think it's a big problem and crucial stuff, and must be addressed to make it commercially a success. Do you know, can you comment on what is the cause of this problem? It is the cause because of weaknesses of the standard, and it can be how to overcome this problem in the real scenarios, like maybe strengthen standards or something. What is the best way to overcome this?
Thank you very much. Thanks for the fantastic question. No, I don't think it's necessarily the standards issue, because the standard facilitate this problem in a way. It made the whole thing open, so different players can bring their own equipment or software or the part or the component, let's say, to this picture. But they are working individually on their own product. So they try to maintain their connections via the open interfaces. But the way that they pass the data, it can cause issues. I think the better investment and the better standardization on these interfaces are the part that they can help for the easier integration and interoperability. But for example, recently again, SRS had a new release. And in that release, some of the parameters changed. But SRS is actually very careful about what they do and the backward compatibility. So everything is working at the moment with SRS. But sometimes some of the vendors do not necessarily provide this. I think it is down to each one of the providers or the vendors of each component to make sure that their component has backward compatibility And if they make sure about that, or when they don't, they actually clearly mention it and maintain the previous version for a while until the users can transit from the existing system to the next system. This is one of the challenges. But I think with the maturity of Open RAN, in a few years, this is becoming much easier because all the players in this market are fairly new. So it's a relatively new technology. The players are very new. So we are all learning together. In a few years, I think it would be better and easier. I don't say that this is going to go forever, we're going to be gone, because even we saw with Microsoft recently, there was a bug and it caused a lot of damage. This happens, but with maturity, I think people can deliver better interoperability.
Okay, Hamid, so we're going to have a break, coffee break now, but I have a few questions, but very short question, very short answer.
Sure.
So the big players, do they want Open RAN or not? Like Huawei?
I don't know.
You don't
I don't know. Possibly they attend the ORAN Alliance. They are in AI, RAN AI Alliance.
Do they want it?
Not sure. Maybe they want it.
It's being recorded, by the way. I mean, if you are funded by them.
I don't know. That's the political answer.
Another question, quick one. You know, which one is more efficient, Open RAN or like a bundled approach, efficiency-wise?
Efficiency-wise, I think that is one thing because they are closed systems. They will be more efficient. They are more efficient at the moment.
Is going to be more efficient. But in the future?
In the future, the Open one is going to be more efficient. The Open RAN, because the innovation is going to be in Open RAN. So the more innovation, the innovation cycle is much faster in Open RAN compared to the closed
So for the
systems.
short term, Open RAN might have disadvantage, but in the long run, it will.
It's going to be.
All right, thank you very much. So we're going to have a coffee break. And after the coffee break, we are going to have a very interesting panel on non-terrestrial network. You heard about non-terrestrial network over the last 2 days. But let's hear from the experts actually who are working on this area and what are they going to say. All right, let's have a coffee break. And before that, actually, we gifts, right? So Ali, we start with you.